Hi. In today's video lecture, we will be looking into attacking reagents. Right? Attacking reagents. In the previous video lecture, we have studied that an organic reaction is a reaction between an organic compound which we call as substrate and an attacking reagent, right? And we know that an attacking reagent is either a positively charged, like a proton is an attacking reagent, or a negatively charged, right, like a hydroxyl ion. Now this positively or negatively charged reagent, right, will attack organic compound, right, at electron rich site or electron deficient site, right, and it reacts with the organic reaction by either accepting electrons from it or by giving electrons to it, right? Because we know that any simple chemical reaction is a reaction between any simple chemical reaction is breaking of bond and making of new bonds, right? So when this breaking or making of new bond takes place, what is actually happening at the background is the exchange of electrons are taking place, because we also know that a bond is nothing but an electron pair. If you remember, a single bond, it's an electron pair, right? And when we say a double bond, it's a pi bond which consists of pi electrons, a sigma bond which consists of sigma electrons, right? So these bonds are basically consist of electrons. Now, attacking reagents. In this video lecture, we would be concentrating on attacking reagents, right, which are like your protons which are provided by source is your acids. For example, hydrochloric acid will ionize to give you hydrogen ion and chloride ion. Similarly, if you have a reagent sodium hydroxide, it will ionize to give you hydroxyl ion, which is again a negatively charged ion, right? So attacking reagents, and these positively and negatively charged reagents will attack organic compounds, right, to bring about a chemical change in them, right? When we say chemical change, the new bonds will form in the organic compound and old bonds will break, right? So attacking reagents are basically, these are positively or negatively charged species. Charged species that attacks organic substrate molecule at electron rich site or electron deficient site, right? Electron rich site, when we say where you have an electron pair that can be donated, right? Or electron deficient site where an electron pair can be provided, right? So basically these reagents, and let's mention one more thing before we go ahead with reagents. Just remember, an organic reaction is a reaction between an organic compound, right, plus a reagent, right? And we call this organic compound as substrate, right? Substrate is nothing but an organic compound, right? And these reagents may be negatively charged or positively charged. When we say negatively charged, like hydroxyl ions, when we say positively charged, like protons, these protons are provided by acids mostly, and this hydroxyl ions are provided by bases, mainly sodium hydroxide, right? So reagents are positively or negatively charged ions, and remember one thing, that these reagents can only attack organic compounds if they also have positive and negative charges, right? So these substrate also need to have positive and negative polarities. Like, let's write down polarities, right? Because we know that a negative charge can only attack at positive site, and a positive reagent or a positive charge can only attack at negative site, right? And mainly in reference to this, these in organic compounds, these positively charged sites, right, are electron deficient. We call these are electron deficient sites, like carbonium ions, the one that we have studied in the previous lecture. Right, now negatively charged sites are electron deficient sites, like carbon ions. I'm sorry, sorry, these are electron rich sites. Like, these are electron rich sites, right? For example, carbon ions, they are electron rich sites. So, right, so they contains a lone pair. Mostly you will see that these contain negative charges, right, or lone pair of electrons, right? Similarly, negatively charged reagents, they also carry lone pair of electrons, right? And this lone pair of, when a reagent, right, that has a lone pair of electron will attack an organic compound at electron deficient site, right? So they will transfer their lone pair of electron to the electron deficient site in order to react and form a bond, right? I hope this is clear. So just remember this basic thing, that organic compound and a reagent, right? So basically a reaction is basically a reaction between a positive site and a negative site, right? Now this positive or negative site, in case of reagents, right, we call these as nucleophiles and electrophiles, right? We'll just understand this. So basically, what is an attacking reagent, right? It's a positively or negatively charged species that attacks an organic compound at electron deficient site or electron rich site, right, in order to bring a chemical change in organic compounds, right? When we say a chemical change, it means bond breaking and bond formation will take place, right? And before this video lecture, just to revise, we have understood that mainly organic compounds, hydrocarbons are neutral, right? That means they don't have any polarities, right? Like here I said, in order for an organic compound to react, right, you should have a positive and a negative polarity, so that the positive and negative reagents can attack these sites, right? So in the previous video lectures, what we were studying are electron displacement methods, right? Electromeric effect, mesomeric effect, right? So due to these electron displacement methods, what is actually happening is there are charges that are getting created in organic compounds, right? So once you have charges on these organic compounds, these reagents can attack, right, those polar sites, positive and negative polar sites, in order to react. Right, now reagents are of two types basically, right? Reagents are mainly of two types. Like I said, positively charged, right, and the second is your negatively charged. For example, you have hydronium ion, right, and this is provided by, like, you say sodium hydroxide is a reagent. So sodium hydroxide in chemical reactions ionize to give you hydroxyl ions. Negatively charged, like hydrogen ions, right, which is again provided by acids, for example HCl, it will ionize to give you positively charged reagent which can attack organic compounds at electron rich sites, right? Because it can accept electrons, right? It can accept electrons and this can give electrons, right? We'll see how it can give electrons, because mainly these nucleophiles, we call these as nucleophiles, right? Or the negatively charged species, right? They have an electron pair, right? If you know the structure of OH, we know that OH, oxygen in OH has lone pair of electrons, two lone pair of electrons that it can give, right, when it attacks organic compounds at electron deficient sites, right? So negatively charged ions, let's first look at positively charged ions. We call these positively charged reagents as as your electrophiles. Electrophiles. Here electro means, this is made up of two words, electro, which means electrons, right, or negative, we know that electrons are negatively charged, right? And philes means mainly this word, the phile, this means loving, right? So electrophiles are electron loving, electrons basically negatively charged, right? So these are negatively charged sites loving, right? So electrophiles will attack organic compounds at electron rich sites, right? That is why we call these reagents that are positively charged as electrophiles. Similarly, negatively charged reagents are nucleophiles, right? Nucleo is taken from the word nucleus and philes we know as loving, right? So these are positively charged loving, right? We know that positively charged sites in organic compounds are electron deficient, right? So these are basically, they love electron deficient sites, right? Negatively charged are nothing but electron deficient sites in organic compounds. Negatively charged sites are electron rich sites. Electron rich sites like carbon ions, we know that carbon ions are negatively charged species, right? So mainly reagents like proton, right, will attack at electron rich site, thereby accepting electrons from it and forming a bond, right? So let's take example of some species that are some reagents, right, basically that are electron rich, right, or an electron poor. That is basically, let's take example of electrophiles and your nucleophiles. And one more thing, since I said that positively charged species are electron deficient, positively charged reagents are electron deficient, and they act by reacting at electron rich site and accepting electrons. They can accept electrons, right? And this definition is same as Lewis acids. Lewis acids are electron acceptors, right? So we call these positively charged electrophiles as Lewis acids, right? We call these as Lewis acids. Lewis acids. Why? Because they are electron acceptors, right? Similarly, negatively charged reagents are called as Lewis bases. Lewis bases, because they are electron pair donors. Electron pair donors, right? How they are electron pair donors? Like I said before, they possess a lone pair of electrons, right? This is again an important point. They possess electron pair, which we also call as lone pair of electrons. that it can donate to electron deficient site. Right? Similarly, you have these electrophiles, right? They are electron acceptors. So they react by attacking organic compounds at electron rich sites, right? They pick up or they accept electrons from electron rich sites, right? So basically electrophiles, these are deficient of electrons and attacks electron rich sites and accepts electrons. Right? So when they accept electrons, they form a bond with organic compounds, right? And when they nucleophiles, when they donate electrons, they are also forming bonds with organic compounds, right? I hope this is clear. Let's take some examples of compounds that are electron deficient or electron loving. We call them as, you have, like we've talked before, hydronium ions, NO2 plus. We know all these are electron deficient compounds, electron deficient reagents. Then we have chloronium, bromonium, right? All these act as electrophiles these can act as electrophiles in organic reactions. Right now there are these are charged electrophiles. These are charged electrophiles. Now there are certain neutral nucleophiles also, right? Neutral nucleophiles like BF3. BF3. This is a neutral nucleophile. If you remember, in chemical bonding we have understood there are certain exceptions to octet rule, right? Exceptions to octet rule means there are certain compounds in which an element has less than 8 electrons or more than 8 electrons, right? So we call them as exceptions to octet rule, since they do not have 8 electrons but still they are stable, right? But they can accept maximum 8 electrons in their outermost shell, so we call these compounds as electron deficient, right? Like in boron trifluoride, boron has 6 electrons in the outermost shell, right? And still this is a stable compound, right? Since it is a stable compound, it has 6 electrons, it can still accept 2 electrons, right? So we call it as electron acceptor. This is a Lewis acid, right? And is an example of neutral electrophile. It does not have any charge on it, right? So when in organic reactions it reacts by accepting a pair of electron, right? Since it can accept a maximum of 8 electrons, right? So this is an example. Similarly, one common example we have is aluminium chloride, right? This is also a exception to octet rule, right? It can also accept electrons, right? And it can also accept electrons to complete its octet, so we call it as an electron acceptor, right? And is an example of, since it can accept electrons, that means it's already deficient in electrons, right? Since it is deficient in electrons, we call it as an electrophile. It does not have any charge, so these are examples of neutral nucleophiles. This is a neutral electrophile. Now let's talk about some examples of nucleophiles. Nucleophiles are like OH, right? The most common example is OH. And if you know, in OH, like here, you have two lone pair of electrons on oxygen atom, and it is these lone pair of electrons that can be transferred. Now first thing, since OH is a nucleophile, that means it's nucleus loving, right? That means nucleus we know is positively charged, right? So it will attack organic compounds at electron deficient sites, right? For example, if this is your alkyl halide, right? So it will break to form an intermediate which is your positively charged, right? Positively charged site is an electron deficient site. So this OH can attack this electron deficient site and will donate its lone pair of electron and will form a bond with the carbon atom of this methyl group, right? This is how these will react in organic reactions, right? So it basically have these two lone pair of electrons, and remember that a nucleophile will always have a lone pair of electrons and a negative charge, right? And it is through these lone pair of electrons that it will react in organic reactions. Now there are certain other examples of nucleophiles as negatively charged nucleophiles as OR, right? All these are negatively charged nucleophiles, right? Then you have some organic nucleophiles like RCOO, right? Acetate ion. These have negatively charged. These are negatively charged ions, right? And these oxygen ions, right? They have a lone pair of electrons in all these. Similarly, chlorine, if we talk about, we know that chloride ion, it's like this. We know it has lone pair of electrons that it can transfer to electron deficient sites, right? And these are negatively charged nucleophiles. There are certain examples of neutral nucleophiles like water, alcohol, ethers, right? Amines, like water, this is water and it has lone pair of electrons, right? Here you have alcohols, it has lone pair of electrons. Here you have ether, right? Oxygen atom has lone pair of electrons. Now when we talk about our NH2 amine, nitrogen atom has lone pair of electrons, right? So all these are neutral nucleophiles, right, that do not have any charge, right? All these are neutral nucleophiles that do not have any overall charge, but they possesses a lone pair of electron, which is a condition for a reagent to act as a nucleophile, right? Because they act through these lone pair of electrons. So all these are examples of neutral nucleophiles, right? And these are negatively charged nucleophiles, right? I hope this is clear. So one thing that we conclude from here is that an organic reaction is basically a reaction between an electrophile and a nucleophile, right? And the other organic compound, the other site where these positively or negatively charged reagents attack are either electron rich or electron deficient, right? So electron deficient, basically these reagents are also, these negatively charged reagents are electron rich and positively charged reagents are electron deficient, right? So for example, if there is a reaction, if we talk about this reaction, the example that we have taken, where OH, right, which is a nucleophile, it has an electron pair, a lone pair of electron. When it will react with methyl chloride, right, we know that methyl chloride will ionize and will form a carbonium ion, which is an intermediate. So this carbonium ion is positively charged. Positively charged means, since it is positively charged, that means we can call it as, since it can accept electrons, right, it is electron deficient, we call it as an electrophile. This is an electrophile, right? And this OH, we know that OH is a nucleophile. So any reaction you talk about, right, because a reagent, right, will attack at electron deficient or electron rich site. Electron deficient sites are electrophiles, electron rich sites are nucleophiles. So basically, like here to OH we call it as nucleophile because it has lone pair of electrons, right? It is electron rich, so it is a nucleophile. So if we talk about this organic compound, it is electron deficient, right? We call it as an electrophile. So basically any reaction is a reaction between an electrophile and a nucleophile, right? Any reaction, right? Any reaction is a reaction between an electrophile and a nucleophile. I hope this is clear, right? Just after all this, we conclude that a reaction is a reaction between an electrophile and a nucleophile. I hope this is clear. Thanks.